So in the second part of chapter 4, we're going to look at different cycloalkanes more closely. Carbon atoms in alkanes are sp3 hybridized, and those carbons enjoy a bond angle of 109.5. If cycloalkanes were flat, what bond angles would be expected? So if we look at cyclopropane, we can divide up the angles. That's going to be 60 degrees. Cyclobutane is 90-degree angles. It's 108 for cyclopentane, 120 for cyclohexane, and it increases as the number of carbon bonds increases. Optimized bond angles, however, most cycloalkanes are not flat in their most stable conformation. You can imagine at 60 degrees, this is going to be very stretched thin. When sp3 hybridized carbons want to be 109.5, it's going to be a very tight fit for the 60-degree angles. So what happens instead, they will change their shape. Cyclopropane does not sit flat. It will get into this kind of conformation. There's a lot of angle strain, as you saw with the 60-degree angles. There's electron pair repulsion between hydrogens and carbons. There's not very good sigma bond overlap, and there is a lot of torsional strain due to this eclipsing hydrogen bonds and the eclipsing carbon bonds. And that's going to be something that we see all the way around the ring. Cyclopropane tends to be very reactive because of this, but it is kind of an interesting phenomenon that you can have this carbon atom with these tight bond angles that does exist. Cyclobutane has a little bit less angle strain, and those bond angles are 88 degrees, which is not as bad as the 60-degree angles in cyclopropane. And it has some slight torsional strain because of adjacent CH bonds are not fully eclipsed or fully staggered. So if you look at this, it's kind of in this V shape here. So it kind of buckles a little bit in order to relieve that strain of being flat. Cyclopentane, these angles are a little bit closer to the optimal value. Remember, those are 108 for the bond angles there. And this one kind of adapts an envelope type shape. So all of these cycloalkanes are buckling in different ways so that they can relieve themselves of angle strain and steric strain. So the next one that we're going to look at and spend quite a bit of time on is cyclohexane. Cyclohexane is considered to have zero ring strain in its optimal conformation, which is the chair. So there's no angle strain, so the angles are going to be 109.5, and there's no torsional strain. All adjacent CH bonds must be staggered. So this is the chair conformation that is adapted by the cyclohexane chair, and you can see that it looks a bit like one of these chaise lounge chairs here. Or you can see that it looks like the Budweiser logo. If you draw the Newman projection of the chair, you can see that all of these things are in this staggered conformation. This is the connecting bonds here between the two things. So if we're looking down two of these angles, this is what we're seeing with the chair. So there's no strain here. It's perfectly anti-staggered. Other conformations of hexane exist, but they're a little bit less stable. So this is one of them, which is the boat. And you can see why it looks like a boat here. The two corners are tipped up, but you can see if we look down the Newman projection at this way, we do have some eclipsing there. This one has no angle strain, and you can look at the different interactions here. So this is the boat, which is less stable than the chair. It's got these flagpole interactions. Here are some more conformations. This is the chair conformation when you go to the half chair, so that is flipping this one a little bit in the upward position. That creates a lot of energy strain because there's a lot of eclipsing bonds here. You have the twist boat, which is a little bit better, and the boat, and it twists again, and then you have the half chair and then the chair in the other direction. So this is just rotated bonds or flipping the chair. So I'll show you a model of the chair. So if we look at cyclohexane, this is cyclohexane, looks kind of flat from here. You can see the different substituents here. So right now, this is the cyclohexane. You can see that chair from the side. So we have this part would be the leg rest. This is where the body lays, and this is the head rest up here. So this is the chair. And if you're looking at that Newman projection down here, down these two angles, you have the staggered conformation. So there's some hydrogens that I left off here. So these are sticking out, so you don't have to see that. But all of the atoms, all of the white and the yellow atoms, these have things that are pointing up, and there's atoms that are pointing down. These are all in the axial position. So if they're straight up or straight down, they are in the axial position. We can do a chair flip. So when I'm doing a chair flip, this gets flipped up, and this gets flipped down. And now the chair is flipped, and all of the groups that were in the axial position are now in the equatorial position. So you can see that there. When you do the chair flip, all the axial groups go into the equatorial position. Their direction stays the same. So before, the yellow atoms were all axial, and they're all pointing down, but I'm going to do the chair flip again. So I'm going to flip this up, and I flip this corner down. So all of the yellow is still pointing down, but they're not all in the equatorial position. And that is the more stable conformation when you have more groups in the equatorial position. So when we draw chairs, there is this chair drawn here. At every corner, the direction that the corner is pointing, there's going to be a group that is axial in that direction. So this is a corner that's pointing up, so we have axial up. This one is a corner that's pointing down, so this is axial down. This one's axial up. Because this corner, this is axial down. And this one's axial down. When we draw the chairs, we're going to start with 3 parallel lines. So I'm going to start with this here. So these are one set of parallel lines. I have another set of parallel lines and another set of parallel lines. So that is how you would draw these. And when you draw the axial hydrogens, you just go and look at the corner. So this corner is pointing up, so I have an axial hydrogen. This corner is pointing down, so my axial is pointing straight down. This corner is up, hydrogen up. This is a corner down. This is an up pointing corner, so that's axial up. I'm going to draw another chair, the 3 parallel lines. So on each carbon, there's also an equatorial hydrogen, and that is, if there was an axial up hydrogen, this would be equatorial down. This one had an axial down, so this is equatorial up. This one is equatorial down, equatorial up, equatorial down, and this is equatorial up. And notice that the hydrogens here, like this hydrogen right here, is parallel to the bonds that are adjacent to it. And this hydrogen is parallel to the yellow ones here. These are all equatorial, and these are axial. So I'm going to draw one more chair so that you can see with all of the hydrogens on there. So all of the axial will be in red. So this is axial up, down, up, down, up, down. Okay, so on every carbon, again, there's an up and there's a down, and there's an axial and there's an equatorial. So this is down, up, down, up, down, up. So each carbon has an equatorial and an axial, and it has an up and a down. So this one is, and it's alternating. So this is down, up, down, up, down. So when you have monosubstituted cyclohexanes, the vast majority of cyclohexane molecules will exist in the chair conformation at any given moment. If they do have energy available, which is about 45 kilojoules of energy per mole, it can flip from one chair to another. So flipping a chair, which I showed you in the video with the model, is the result of only carbon-carbon bonds rotating. The Newman projection below shows how flipping occurs only through rotating bonds and how it affects the axial or equatorial position. So in this chair here, we have the equatorial X, and when you do the chair flip, so you're rotating these bonds in and these bonds in, that equatorial group becomes axial. Or in this case here, we have a group that is axial. It undergoes the chair flip. and then it becomes equatorial. So in this chair conformation, the purple group is a methyl group, a CH3. It is in the equatorial position. So you can see this is what it looks like from above or flat, and this is from the side. So right now, all of the yellow balls here, these hydrogens, are in the axial position, as are the white ones here. So the methyl group here is in the equatorial position and is pointing away from everything. And there's not very much interaction between these hydrogens and anything else. But now I'll do a chair flip. So when I do the chair flip, this is going to get rotated up. This one gets rotated down. My hydrogens that were all in the axial position before are now all in the equatorial position. And this group is now in the axial position. If I had put my hydrogen in here, which I didn't, you might be able to see that when this rotates, there is the personal space bubbles here that it might interfere with. And certainly if you had other substituents here that were bigger, that would interfere with that. But when you do the chair flip, everything that was axial becomes equatorial, and everything that was equatorial becomes axial, as you see here. If both versions of the chair were equally stable, you would have a 50-50 mixture of axial and equatorial, but you have steric crowding, which is also referred to as diaxial strain. So this is that diaxial interaction, which is also the same thing as steric crowding. So you would actually see 95% of this methyl cyclohexane in the equatorial position, compared to the axial position, which is only 5. So this is that space bubble that I was referring to. These H's here kind of start bumping space bubbles when this is in the axial position. So as your group size increases, the amount of diaxial interactions is going to increase quite dramatically. So if you have a tert butyl group on there, 9,999 parts of that solution would be in the equatorial position and only 1 in the axial position. So this one is a good way to lock it in a certain position by putting a tert butyl group on there. So if you have multiple substituents, you can use solid or dash wedges to show the positioning of the groups, and that shows them in either axial or equatorial position. So what you can get from this flat cyclohexane is that we have a chlorine group. This chlorine is pointing up. This methyl is pointing down. So the wedge is going to tell us up. This tells us down. To draw the chair, I'm going to start with your parallel lines. And I'm going to number the carbons so I know where to put my groups. Chlorine is in the up position, which means at this corner, this is pointing up. So if it's pointing up, that means my axial is pointing in the same direction as the corner, which will be axial up. So this is chlorine. And at carbon 2, my methyl group is down. And this is a corner that is pointing down, so that it's going to be axial down. If we do the chair flip, what you're doing really is, this is where it's getting rotated. This is where it's getting rotated. This corner is going to get rotated down. This corner is going to get rotated up. And I'm going to draw my lines the other direction because it's now been flipped. Since this corner is now down, this is now carbon 1, and this becomes 2, 3, 4, 5, 6. Carbon 1, my chlorine was up. The direction of the chlorine stays the same in the flipped version. But because this corner is now pointing down, that's going to be axial down, so this becomes equatorial up. And the methyl group that was down before is still down, and it's going to become equatorial. So this is axial, axial, equatorial, equatorial. So when performing a chair flip, the direction of the substituent stays the same. But axial groups become equatorial, and equatorial groups become axial. So my chlorine was up, it's still up here. It went from up to up in the direction, and then the axial became equatorial, and the same thing with the methyl. So methyl was pointing down, it's still pointing down, but it went from axial to equatorial. Practice drawing these chairs again. So I'm going to start with my parallel lines. At 1, this is up, this is down. My corner is up here, so this is going to be axial ethyl group. And then at 3, I have a down. This corner is up, so that's going to be axial up, so this will be equatorial down. So that is 1. If I do my flip, this becomes 1. This is still going to be up, but it will become equatorial, and this becomes axial. So axial, equatorial, axial, equatorial. The one that is more stable is the one that has the group, the larger group in the equatorial position. So between ethyl and methyl, it's 2 carbons versus 1. This is the one where the ethyl is in the equatorial group, so that one is the more stable one that is preferred. All right, for this one, 1, 2, 3, 4. And you don't have to number exactly as I did. If you started your 1 at this carbon here, that's fine as long as they match each other. So at 1, I have a tert butyl group. That's axial up. This is up also. This one will be equatorial up. Then I do my chair flip. So this becomes equatorial, and this is axial. So even though these are both pointing in the up direction, in the chair form, one is axial and one is equatorial. But when you do the chair flip, the axial becomes equatorial, and the equatorial becomes axial. And the more stable one is this one here. We have a super large tert butyl group. That one's going to be preferred being in the equatorial position. One other thing to note is direction of substituent does not predict axial equatorial. So again, if just because they're both up does not mean that they will both be axial or both equatorial. That just refers to the direction that it is pointing. Okay, so with that, if you have a disubstituted cycloalkane, we need to start using or getting the habit of using the prefix cis when there are 2 groups on the same side of the ring, or trans when they're on opposite sides of a ring. So these CH3s are both pointing in the upwards direction, so this is a cis. 1,2-dimethyl cyclohexane. These are on opposite faces of the chair, or the cyclohexane. One's on top, one's on bottom. This is trans 1,2-dimethyl cyclohexane. So if you were to draw them flat, it would look like that.